So hi everyone, welcome to the webinar series organized by SEAM this afternoon. So today we're going to have Professor Ivan Ko sharing with us. Professor Ivan Ko is the Enabling Capability Director for Advanced Manufacturing and Fabrication at RMIT and is a Chief Investigator with SEAM, leading a project with industry partner Roma Engineering in Sydney. His research interests are in additive manufacturing and other advanced metal fabrication processes, surface finish, preservation, and corrosion inhibitors, nanostructures and nanosensing, modeling of materials, and life prediction of materials. So today, Ivan's going to present on challenges in molecular design of protective paint films for actual service conditions. During the presentation, if you have any questions, feel free to start posting them up on the Q&A chat. And we're going to have a Q&A session for about 10 minutes after his presentation. So before I hand over to Ivan, may I just ask everyone to be on mute while he's giving his presentation. So over to you, Ivan.
Thank you. Jump into the presentation. As the title says, we're going to focus on two things, how we design materials at the molecular level and how we predict whether they will perform in service. Although I have the pleasure of being a CI with SEAM, as we can imagine, SEAM is only a little bit old. Most of this work is done prior, and a lot of this work has been done in my prior employer, which is CSIRO, in collaboration with Boeing. So I'd like to acknowledge my CSIRO ex-team, my Boeing partners, and also my current team, the Rapid Discovery Fabrication team and SEAM at RMIT. I am a little bit restricted in what I can present because a lot of this work was commercial, and I'm only presenting work that has already previously been presented. So we want to combine computational design, rapid inhibition, and robotic experimentation. So we can design at we're primarily focused on wanting to understand sensory materials and materials that can respond to the environment. As soon as we begin to design at the molecular level, even if it's only part of the structure, we literally get tens of thousands of different design choices for our materials. So the question is, how do we select what choices to make? And how can we do that in a fast way? We're now, rather than selecting from maybe 10 or 20 choices, we're selecting from maybe 10,000 or 20,000. Well, there's two methods. One is to do it virtually. So that's to do it by molecular modeling combined with atomic and larger scale modeling, so-called multiscale modeling, or to use high throughput or at least rapid testing to sort through this high level of design complexity. And why is that necessary? This talk, as you gathered from the title, is going to be predominantly about corrosion inhibitors. Now, corrosion inhibitors are put in the primer of a paint film, or they may be used to passivate the metal surface before the primer goes on, or they may be used as corrosion inhibiting compound sprayed on a surface, or if it is a pipeline or something like that, they may be used in being ejected into the liquid that the pipe is carrying. So there's a number of ways we may use corrosion inhibitors. In our case, we're predominantly talking about them in paint, and therefore they're predominantly in the primer. So this was work done by Tim Harvey at CSIRO, looking at a family of inhibitors called the capto compound. It's quite complicated, but all that I want you to really see that is we change in small ways the inhibitor chemistry, we can dramatically change whether it is a corrosion inhibitor or in fact whether it promotes corrosion. So just this up on the left-hand side is the different molecular structures, and down the right-hand bottom is the inhibition efficiency, where something is on the top, and I have to say, between 90 to 100% efficient. That's a very good corrosion inhibitor, which will cut corrosion down to anywhere from 1 to 10%. If we're on the bottom of that graph, though, we're actually promoting inhibitor. And we can see that if we go from inhibitor D with the file group to inhibitor E without our linker group, we dramatically shift the performance and go from quite a good inhibitor to a corrosion promoter. And similarly, other small changes with the molecular structure dramatically change how the inhibitor performs. So we need to get not only the right type of inhibitor, but the right isomer amongst the different families. So we've traditionally done that by high throughput experiment. This was work that was developed by Paul White at CSIRO, and he used what is called the high throughput well technique. The wells, you put a saline solution in it, and you put the corrosion inhibitor in it. And then you see the color change after 24 hours. Where the color has not changed substantially, there's been very little corrosion, and that's given a low number, indicating that protection of the surface was effective. Where there's a lot of change, a lot of corrosion, product builds up, that is showing that corrosion inhibition was not effective, and it's given a high number. So you end up with very complex diagrams like this. This is deliberately made small, firstly to show you the amount of data, and secondly because this is data derived from Boeing by CSIRO and is confidential in nature. But these charts look at, in one of these squares here, we are literally looking at 1,000 tests. And so this is one test on one material, this is one test on another material, and then there are synergies between different tests. So you're literally at 4,000 pieces of data, 4,000 tests in this diagram. And that allows us to spy out the green areas where inhibitors are forming well, and down below, spy out the green areas where combinations of inhibitors are forming well. By using these methods, we can relatively quickly, this program still took a number of years, find what the best inhibitors are, and very importantly, what the best synergy between different inhibitors are. If you remember what we said before, where we're green on this little chart, I have numbers like 1 and 2, the inhibitor is very efficient. Where we're up at 8 or 9, and then we're not stopping corrosion. And we can display that in this little graph down the bottom. The green numbers are, green squares are where inhibition is efficient, and the brown and purple ones are where they're not efficient. What this shows is by combining an organic inhibitor, its structure's been taken away. With an inorganic one, we can get very strong synergies. So by itself, the organic inhibitor is effective to about 10 to the minus 4 molar in concentration. And the inorganic is not really effective at all. But combined, we can get the combination to be effective when the organic is 2 by 10 to the minus 5 molar, and the inorganic is 5 by 10 to the minus 5 molar. Why are we so concerned about getting inhibition at low concentrations? Well, there are two reasons. Firstly, in general, as we raise the concentration, the efficiency will remain high. And secondly, when you put your inhibitor in a paint, it gradually leaches out. So the life of that protective paint film is tied to the minimum concentration of inhibitor required to protect the surface. Now, I wanted to show you the physical surface, but I had to take it out for confidential reasons. But basically, when we do immersion tests in these solutions for a period of 30 days, the aluminium plates come out without corrosion. Now, we haven't mentioned before what type of plates we are, so let's step back and mention that now. The inhibitors we're using in the aluminium systems are for structural aluminium. As we all know, aluminium is quite corrosion resistant in its pure form, but to use it in aircraft, you have to add copper and iron to develop the intermetallic particles that increase its strength and make it a pure alloy. Unfortunately, by doing so, you also make it susceptible to corrosion. And this is why we need the inhibitors in the paints. And this is why these results where we get virtually no corrosion after 28 days and in this test get very low values of surface change can therefore protect our aluminium surfaces. Up to now, those surfaces have been protected by strontium chromate. And strontium chromate has done a marvelous job over the last 50 or 60 years. Unfortunately, strontium chromate is a human toxin, and so is being rightly phased out. So all around the world, people are looking at solutions to have non-toxic and at least close to green inhibitors to replace strontium chromate. Okay, so by using high throughput methods, we can discover inhibitor systems that work in the laboratory. How do we know that they're actually going to work in field conditions? In particular, how do we know that if we paint an aircraft with a paint system containing an inhibited primer, it will protect the aircraft for the period required, which is generally around 20 years. Now, with strontium chromate, we have a lot of experience, and we know from experience that it will work. We can do long-term tests, and it is mandatory to do at least 2 years of in-field testing for new paint systems for aircraft. However, we only want to go to that massive expense with the final down-selected inhibitor. All the rest, we want to be able to test virtually and know whether we're likely to get that 20-year performance. So how do we go about doing that? The system that we developed, and this was again between CSIRO and Boeing, was to use multiscale modeling to connect the corrosion and environmental processes from the molecular scale literally up to the continental scale, so that we could be confident that we could accurately predict how an inhibitor in a primer on a paint film on an aircraft would perform over time. So these multiscale models contained a molecular part to look at the molecular features, the HOMO, the LUMO, the dipole, distribution around these molecules that you saw before. They had part transport models to look at how the inhibitor would be transferred through the paint system and to cracks and other defects that occurred that were corrosion sites. They had a model looking at the alloy structure and looking at where those intermetallics, which provide strength but also act to stimulate corrosion, are. So that was the basic material structure. Then we needed to know what the environment was. So we then started with looking at the flight path for the aircraft. For each different flight path, we looked at the pollutant level, aerosol levels, both marine and industrial that might impact on the aircraft, and the microclimate that would be developed in the aircraft. We combined then the microclimate and the material system to look at how corrosion might occur and then how that would progress over time to lead to damage. So combining these systems together, we could, to a reasonable degree, predict the life of the inhibited paint film. So what were some of the components? First was the molecular modeling. We use DFT and other modeling to look at a number of features of our molecules. They're basically heterocyclic molecules with linker groups on them, and we could develop this DFT and do it quite rapidly, actually, and then link it to a supercomputer and build out our base of molecular properties. One of the most famous molecular properties in the literature is the HOMO-LUMO gap. This is the highest occupied molecular orbital and the lowest unoccupied molecular orbital. The difference between that gap basically tells you, is the molecule electrophilic or not? Will it transfer its electrons to the metal surface and therefore bind to the metal surface? It was considered by many researchers that that would give us a very strong indication of whether the corrosion inhibitor would work or not. So we tested that with our expanded database generated by the more rapid testing and the more rapid molecular modeling. And unfortunately, we found that when we plotted corrosion inhibition against this fundamental gap, we found virtually no correlation at all, despite what was in the literature. So this doesn't mean that it's not important, but it's not sufficiently important to describe the variation that occurs in corrosion inhibition. So then we look at, well, how else can we model corrosion inhibition? Where are we? Okay. So we then just say, well, maybe we can incorporate more different parts of the molecular structure into our models. Now, again, I need to step back and explain one thing. In connecting the models together, and in particular in connecting molecular models and electrochemical models, at the moment we do not have a rigorous process-based models that can do that. So we need to use statistical or neural network or machine learning approaches, if you like, to connect that. And so what we do is we put in the molecular features on one side of our model, and we put in the electrochemical properties on the other, and try to construct a neural network next to them all. So we tried to do that with the HOMO-LUMO gap and purely DFT modeled parameters, and found that it wouldn't work. From then we said, let's have a look at some of the characteristics of the molecule. And we used a program called SMILES to pull out a large number of features of molecules. We ran this through the neural network against the electrochemical properties, and we then did come up with a good neural network generated model. And it showed the type of features that provide good corrosion inhibitors are things like oxygen atoms, nitrogen atoms, thiol groups. And for those of you that are chemists will understand that they can generate lone pairs, and those lone pairs can bind to the metal surface. And this is an example of the output from one of those models, the inhibition efficiency actual against the predicted one, using that combination of DFT derived parameters and SMILES derived molecular features. And we did obtain quite good models. And as we mentioned before, it tended to depend on whether there was a thiol group, a sulfur group, an oxygen group. Once we have the connection between molecular structure and electrochemical structure, we then need to know what the environment that paint film will be in. We had the advantage, particularly in the aircraft area, that we had been looking at aircraft corrosion in conjunction with different partners by placing sensors on aircraft. This is a diagram here with the large sensors of the actually part of a RAAF aircraft. This, in fact, is a C-130, where we placed sensors in this mock-up and put them in the lab, and had the same sensors in a C-130 transport aircraft. This is one of the problems implicit in this, which we'll talk about later, is these sensors are quite large and they're actually not measuring explicitly the corrosion of the surface. They're measuring corrosion on little coils or little bits of metals that we hope will simulate the surface. But we can measure the microclimate and the corrosion rate in the surface. As we mentioned before, we can design a flight path to know where the aircraft is, or alternatively, we can look at a test. Test is a salt spray test. These little diagrams show how water is forming down the surface, and so we can find out what the microclimate is. In this case, we're simulating a scribe in a paint film in a neutral salt spray test, and we're looking at where the droplets are. So this is the paint film in this one of these little squares, and the little scribe is here in blue. And we could look at whether inhibitors can go from the paint film into the little moisture area, and where we can get inhibitor into the moist area, it's green. Where inhibitors can't reach the moist area, it's red. And so we can do a time map, a time and position map of when the inhibitor is protected or not. So getting back to the aircraft rather than the laboratory test, we could use our data on, we've got a large amount of data and microclimate and salt levels and models of how salt is distributed around the country, so we could model the microclimate that the air goes through. This is the purple and coloured square is a estimation of airborne salinity across Melbourne, and our aircraft is taking off from Tullamarine. Basically, we find that close to the sea, the red areas where airborne salinity is high, but the salinity is trapped by buildings and other structures. So by the time we get out to Tullamarine, it's dropped down to ground. But as the aircraft goes up into the sky, it goes through that scavenged area, up into the plume of aerosol, and picks up aerosol that will slowly but surely corrode the aircraft. So now we understand the microclimate that the aircraft goes through. Now we need to simulate the metal structure, and we do this. We did a lot of work looking at atomic probe to understand what the structure of our aluminium alloys were. And here in the light colours, you can see all the different intermetallics that are providing that strength to the aluminium, but are also acting as corrosion points. And we can generalize this into a generalized microstructure, which we then did. And for each of those intermetallics, we build a little corrosion model and look at how the corrosion rate occurs, and also how the inhibitor can slow down that corrosion rate. Having combined all that, we can then look at the life of the inhibited paint film, and we can look at it as a function of the flight pattern of the aircraft. Now, this was a particular, not so much test, but a problem to they had the same aircraft flying on two different aircraft routes, but they found that one of the aircraft was corroding at a faster rate than the other, and they couldn't understand why. So they came to us and said, the aircraft, airplane number 2 flying on these routes is not corroding, where aircraft 1 flying on these routes is. So we put that into our system, and we found that this was the probability of pit growth from corrosion on aircraft 1 in the red, and in the blue is aircraft 2. So you can see, just as we were told that the corrosion was occurring much faster on aircraft 1. Analysing the pattern, it's because aircraft 1 has these excursions down in much more into southern Australia. The roaring 40s are coming across Australia, hitting the coast of Tasmania and Victoria and South Australia, generating a lot of marine aerosol and therefore a lot of corrosion, whereas aircraft 2 spends a lot of time in Western Australia where it's dry, there's very little salt aerosol and corrosion is low. So we were able to go back to our partners and say, no, this does not represent more defects in the aircraft, it is just the different patterns. So, next issue I want to talk briefly about is that traditional faster experimentation did have a lot of advantages, but it has a couple of disadvantages. Firstly, as an electrochemist, it's not particularly satisfying because it doesn't give you an electrochemical data. So I'm going to skip a little bit of this. We had developed at SIO and are redeveloping at RMIT an electrochemical robot where we have a robot head that goes between each of our cells. It can measure 20 cells at once, and therefore we can generate that rapid experimental data, but we can do it by getting full electrochemical data and therefore having a lot to analyze as well. Going to skip this session, very interesting, but I'm running out of time. Next area just to tack on, I mentioned before, all our sensors to measure corrosion are actually not measuring corrosion of the metal itself, but they're measuring corrosion of a physical sensor adjacent to metal. One way we began for this was by developing nanodots. A nanodot might be a semiconductor dot like cadmium, tellurium, zinc sulfide, or carbon dots. Basically, what these dots are is they fluoresce at particular frequencies, and when particular metals, ions, come in contact, that fluorescence drops. There are particular ways to sensitize these dots for particular metals, but basically we could use the fluorescence of a dot to measure metal ion concentration. And we've done that with our partners to look at how corrosion is occurring in a paint film and to have a direct measure of corrosion and a direct measure of the life of the film. We could also put that on a little chip and develop a multi-analytical sensor as well. That's probably a story for another time. I'll skip that. Interesting it is, but I'm running out of time. So molecular design, if we're going to have it, we need fast methods of appraisal. We also need to know how the component will actually perform in service. Computational design can connect our molecular modeling to engineering scales, and it can sort out what would be possible viable inhibitor solutions, although we'll still have to go and do the compulsory 2-year testing on the ones that we down select. The high throughput is providing a rapid screening method to refine molecular structural selection, and the robotic experiment can do the same without loss of data. So what do we want to do in the future is build computational systems that can integrate new models and data across the globe, build robotic systems that can be integrated in computational systems to self-build models. Skipped over that part. Integrate our data sensing into robotic systems and build new materials that can measure, sense and respond on the nanoscale. So as many researchers have done, I've talked in a fairly rosy way about what we've done and what is possible. As this is amongst our friends in SEAM, I'm actually now going to go and highlight some of the issues. Firstly, on the molecular modeling, we showed you that firstly the HOMO-LUMO is insufficient, and then we added different molecular features. What we nearly understand inherently what the spatial geometry developed is. This is some work done by Michael Fernandez at CSIRO, looking at how we can use COMSAR to look at the geometry of different features, the iso distributions and dipole distributions, and see if that geometry can provide us a more nuanced level than just single features like HOMO and LUMO. The other thing we've mentioned is we can't actually at the moment connect in a process-based way molecular structure and electrochemical structure. And one of the reasons is the physical gap between that is huge. So it's not surprising, a lot of across this. So we need to try and refine the gap by making our experiments. Generally, we measure inhibition either on a exposed plate, which is 100 by 150 millimeters, or on a electrochemical coupon, which is a bit smaller, but still 20 mils, which is much bigger than our DFT experiments. We could do refined analysis, local analysis on our features, and we could also expand out our DFT modeling to try and close that gap. The molecular modeling we did was in vacuum, and therefore did not take into account the full, or did not take into account the complexity of binding to surfaces or the complexity of solvation and hydration and deprotonation. Not very many molecular processes could not be taken into account. Lastly, this is a fib sim looking right down here at this edge here, which looking at how a inhibitor layer builds up. This square, I hope you can see where my arrow is the metal surface. Right above it is the inhibitor layer, and above that is a protective layer placed on the fib in order to look at it. And here's some EDS of the layer it is. This is just a quick way to show we're not exactly sure what these protective films are. They tend to be 10 nanometers or larger, so they're not just a simple monolayer of inhibitor. They're a complex layer that we need to explore more. Further, I talked a little and showed you this slide before of what actually happens on a surface. We have different intermetallics. They can behave as anodes or cathodes, but in general, our inhibition value is just for the whole surface. And it ignores the fine features of what the individual inhibitors are doing. So we need to drop down to this fine layer of electrochemistry. And our experiments were derived from electrochemistry in solution, when in fact corrosion mainly occurs by fine droplets. The droplets are in two ranges, 2 to 5 microns is the deposited aerosol, or 0.5 to 3 million if they are raindrops. Whereas experiments, as we mentioned, in solution on microliter amount. So there's quite a different scale between our electrochemical test and actually what happens in surface. Lastly, I talked about us understanding the microclimate in aircraft. That's true, but only to approximation. Our work and all the work preceding to us places sensors in aircraft and looks and predicts the microclimate based on those sensors. Assumes that the space in an aircraft is generally uniform. This is some CFD modeling done by Patel, looking at the air distribution and the relative humidity distribution in an aircraft, And what you can see is it's very far from uniform. So if you were to be placing your humidity sensors and your wetness sensors at one point, you can be measuring quite a different condition to somewhere else in that space. So we need to refine these models as well. So where have we got to? We have developed an original computation of the framework. That's a bold step forward. However, there are problems. We need to extend our molecular modeling. We need to refine our electrochemical experimentation. And we need to know what exact test methodologies will give us the best prediction of inhibitor and surface. We are actually working on this. We have both PhD projects, but also a major project with BASF. So we are working to refine our molecular modeling to better consider the complexity, sorry, I went too fast, of the molecular form and surface interaction. We are working to reduce that nano gap, both at the experimental level and at the molecular level. And we're hoping to build a new conceptual framework that gives a deeper understanding of the mutual scale and interrelated processes that control corrosion. So I will finish the presentation here. I hope to illustrate that this is a cup which is 2/3 full. We can do quite good predictions of life, real service life of inhibited paint films, but there are a number of problems to resolve to improve the felicity and reproducibility of both the experimental work and the modeling work. So I will leave that presentation here, and I will then end the show.
Thank you, Ivan, for the very interesting talk. We have a couple of questions coming in, so we'll start going through them. In the meantime, if any of the audience have questions, continue to post it in the Q&A session. So the first question. Right. So this is from Reza Pavesi from Deakin University. Her question is there a capability to utilize ultra-high resolution techniques such as atom probe tomography to investigate and validate atomic scale simulation of inhibitor microstructure interactions and adsorption mechanisms?
Yes, it is possible, particularly the microstructures we develop by using the atom probe and to understand that. It's hard to make a generalization because it depends upon what the atom probe will do to the organic bound to the inhibitor or bound to the surface. But yes, in general, you can detect, for instance, sulfur on the metal surface, and the sulfur is indicating the presence of organic file groups. So atom probe is useful to find out where the inhibitor is bound.
So this next question is from Niraj Sharma. Can we simulate the corrosion rate of aerospace material depending upon the environment it passes through? In vitro testings are how much successful for this?
So certainly we can, to a first approximation, simulate the corrosion rate in aerospace components. Yes, that was the aim of the project, but I'm a little bit confused by the in vitro. That's not a term I would normally apply to aerospace.
Okay. This next question is from Andrew. How is one going to measure electrochemistry behavior at nanoscale level?
Okay, so we have a few approaches to do that. One, we are working with a Spanish group. In fact, they're called ICN2. They developed the DFT program Siesta to work with them to see if we can put more potential effects into DFT code. So one way is to try and model it, but try and model it by upgrading with the inventors of the code systems. The other reason why we're very interested in the fluorescent molecules is because they are at the nanoscale and they will fluoresce at the nanoscale. They would not be able to tell us the exact electrochemical process, but they can mark where it's happening. The fluorescence will change in the presence of metal ions, which are generated by the electrochemical process. So there are a couple of ways, both modeling and experimental, we may be able to do it. Obviously, what would be attractive is more direct studies in situ microscopy, for instance. That's very hard to do, and it's actually quite hard to try that. There have been some work done in the UK using synchrotrons to look at in situ work. That is a promising area as well. So it's definitely at the edge trying to look at direct experimental measurement at that scale, which is why inferring things from modeling is our current major focus. But taking the scale of electrochemical measurements down to the finer micron scale rather than the whole working electrode scale.
So this next question is also related to the previous one. This is from Chris. What are the limitations of dots? For example, physical size, temperature, stability. Do they need to adhere to the codings, etc.?
All right, so the limitation on dots, well, the size is about, depending on the dot, 2 to 10 nanometers, but you have to image them. So the limitation on resolution of a dot-based system is how well you can image it. There are issues around stability. It depends on what type of dots you're using. There are definitely some issues around selectivity. Dots can have ligands attached to them to try and make them specific to particular metal ions, but it's quite a complex process and it's quite difficult to make them specific just to one metal ion.
So Chris also asked another question that would be considered a career guidance question. What single piece of advice would you give to an early career researcher?
Right, career advice. Okay, so I think, look, although I've pointed out the holes in our own work, I would say it's good to be bold. It's good to try to tackle difficult problems and try to derive the best solution you can while still being aware and not covering over the limitations and the I wouldn't say defects, but I would say work still to be done in your own solutions. So be bold, but don't be arrogant, I guess.
That's really good advice. The next question from Moss. So he mentioned that he appreciates the role the computational modeling can play in reducing experimentations and hence save us costs. But the question is, how do you qualify your theoretical DFT models in the first place? If you could please comment on this, that would be great.
Okay, so there are I'm not actually the DFT expert. In that program, Michael Breeden was the DFT expert, but you use your DFT to calculate well-known parameters. And if your DFT is giving parameters that are well known for the system, you can have some faith in that you're doing it correctly. So you calibrate against answers you already know is the basic question. So that's the first stage. And then after that, you just need to use your chemical intuition to see whether it's giving you the types of values that you would expect. So calibration and then intuition, I guess, is two answers. But also there are a number of different DFT systems, some more accurate than others. And so what is often done is to use a very accurate system, which will take a lot of time and cost a lot in terms of supercomputer usage, and compare a more a lighter DFT system against the more intense DFT system to see how much fidelity you're losing by going to a more efficient system.
So just following up on that, Krish has two questions. So the first one, in the molecular dynamics setting, what were the number of atoms used and the force field used in a typical simulation? And could the results from first principles of DFT and MD be reconciled effectively?
Okay, so I put it there as a way forward, but we did not actually do MD. So I can't talk about the MD structure because that was a recommendation of how we should go forward. We're still actually debating whether MD is a useful way to do or not. I can't honestly remember the structures, but we have a range of papers out there. If anyone is really interested, they're very welcome to go and look at those papers, and they will see what structures we used.
The second question from Krish, what were the differences in efficacies between the cadmium-based quantum dots and the carbon dots for sensing applications?
So I couldn't quite hear. Could you say that again, please, Ruth?
Yep. So what were the differences in efficacies between the cadmium-based quantum dots and the carbon dots for sensing applications?
Okay. So it is quite different. The semiconductor dots have a better quantum yield. They're more reproducible, and they're can be more stable depending on which dot you're using. The cadmium tellurium are probably the best, the most stable. The zinc sulfide are less stable. The carbon dots are more variable. They're less efficient, and they need to be controlled more in the manufacturing process. However, it's not really terribly appealing to say you want to do environmental sensing or you want to reduce toxins in paint and then add in cadmium tellurium. So although it's actually probably not a big factor really, because dots are incredibly small and the amount of toxic material you're using is tiny, it's not a good look. So we moved away from the semiconductor dots to the carbon-based dots. And we do lose yield, and we do lose some stability in doing that. That is very true.
Okay. The next question, how do you decide you have results good enough from each model to proceed to the next stage of development?
Yeah, that's a problem. And it's a problem also trying to it's a problem trying to validate the whole model as well. We did put panels on planes, and we have a small amount of data of panels on planes, so that we can we have some ability to validate the final system. Each individual component, they vary quite a lot. As we've already discussed, validation of DFT is quite hard because we can't get the data. We can do some experimental data to look at binding and things like that, but it is quite hard to do that. Other parts of the model can be reasonably easily validated. We did quite a lot of work on how inhibitor leaches out of paint, for example. That's quite easy to test. We just do leaching experiments. The electrochemical models that we built, again, they're reasonably easy to validate. We simply do electrochemical experiments and see if our electrochemical models match them. Again, microclimate models, because we had a lot of data from sensor on aircraft, they're again quite easy to validate. So depending on the scale, validation is reasonably standard or incredibly difficult. The finer the scale, the more difficult validation becomes.
The next question is from our your views on high entropy coatings and their corrosion phenomenon for scramjet applications.
I don't know. High entropy coatings isn't my specialty. We're doing a little bit of work on high entropy alloys for a totally different application with Cyro, but I'm not going to declare myself an expert on that one, when in SEAM there are others who would be much better to answer that than myself. So I'll leave that to other SEAM experts. Maybe Vesta can pass that on to someone else in the SEAM community.
We'll hear back from Vesta now. Okay, the next question is from Peter. So is chemical corrosion rate higher when the metal is under mechanical stress?
Yes, and that is a limitation in our models. We did not include mechanical stress. We assumed actually that the paint film was already cracked from mechanical stress, which it very frequently is, but we didn't add mechanical stress as an additional one. What we did was grow a pit, and then we did then look at fatigue modeling under mechanical loading of the pit. We didn't look at the synergy between corrosion and mechanical stress, and we didn't look at the synergy between fatigue and corrosion. And one should. We don't have the situation, because we did examine different failures where you have a true stress corrosion or corrosion fatigue simulation. So we're not in that ambient, but that doesn't say that there is not some contribution from one to the other.
This is also from Peter. How do you ensure the inhibitors are homogeneously distributed at the metal surface?
It's really difficult. So the part of the program that I didn't talk about is partly because of IP reasons, part because of time reasons. Once we selected the appropriate inhibitors, we put them into paint films, and we did salt spray testing and other testing of those films. A big challenge that is not in this talk is how you get a good distribution of inhibitor into the films, and how you also stop the inhibitor reacting with the polymer film. Now, I'm going to give a plug now, and Vesna can probably remind me on the date, but later this month, in conjunction, SEAM in conjunction with Materials Australia and the ACA is going to have a seminar, and we will have an expert from BASF talk about exactly this issue. So if anyone is particularly interested, come to our seminar and you will learn how to put active molecules in organic paint films and get good distributions. Vesna, do you remember the date of that?
I do, thank you, Cole. It's the 25th of August and the details are available on the SEAM website.
Good. Thank you for that question. It gave us a good plug.
Okay, so this is the last question from Andrew. MD is too computational intensive to be useful from memory, but my question is, what are the corrosion protective materials that have attracted your interest?
All right. So we do work on a number of systems. We're doing a lot of work now in the last 5 years, 10 years on inhibited systems. Inhibited systems not only for aluminium, but for steel and galvanized steel. It's primarily been the organic inhibitors because others like the chromates and the phosphates are being banned in different places around the world. So a lot of work on those, although having said that, we have done a fair bit on phosphate conversion as well and cerium conversion systems. We've done a lot of work on zinc-based systems, and my own team, particularly Dr. Selbo Chen in my team, is looking a lot at microalloying in magnesium in order to produce biocompatible materials. And we're also doing work on biocompatible titanium mixtures and titanium tantalum mixtures. So quite a range of applications, from aerospace to cars to biomedical.
There was another question by Aru. Have you considered thermal oxidation while selecting inhibitors?
No. Most of the stuff is at room temperature. The most of the surface conditions, some of them can get very cold, but they generally don't get that hot for the systems we're talking about.
Okay. And I think that concludes our Q&A session. We're right on time. So let's once again thank Ivan Ko for the very interesting talk and such a interesting Q&A session as well. Thank you to all for joining us in this webinar. If I'm not wrong, I think this webinar is recorded and it will be posted on the SEAM website. And just to remind everyone again, the next webinar would be on the 25th of August. Like what Ivan and Vesna told us just now, it's a presentation on surface engineering from an industry and academic perspective. We'll be having Dr. Thomas Schläfer from Laserborn, Professor Chris Byrne from Swinburne and SEAM, and Dr. Patrick Hill from WSF Coding to give us a talk on that. So I look forward to seeing everyone there. So thank you, everyone, and have a good day.
Okay, thank you.